All right, Physics 2. So, what I like to do for the end of chapter 23, where we get into a little bit of optics, which is one of the big applications of these light waves that we've been building towards, is I just like to do a really nice overview of a lot of the topics that they cover. And so this is meant to go in conjunction with the reading that you're already doing in the book, and it will really highlight a lot of the key components to understand with doing these types of equations. So, and my personal opinion is the book is a bit complicated when that explanation isn't as necessary. All right, so go back here and we talk about the penetration of Earth's atmosphere. Earth's atmosphere is transparent only to particular wavelengths, and thankfully it's transparent to visible light, which enables us to see and live and breathe. Goodness. It will change speed. So light does not travel at 3 times 10 to the 8 meters per second in every material. It actually slows down. So you have never seen light that has traveled at 3.8 meters per second because you've never seen light inside of a vacuum. I've actually, no. And if you are looking into a vacuum, you're looking into it through a window, which has then shifted the speed of light through it. And we'll get to that soon. Object. A blue object means it's absorbing all wavelengths of light except for it's reflecting blue. So you see the blue light that's being reflected off of that object and it appears blue. A red object, although I feel like it looks pink on the screen, is absorbing all wavelengths of light except for red, and so you see that red light that's being reflected. And so black objects, of course, absorb. They're fully opaque. They're absorbing all of the different light coming in, so they appear black. White is, of course, a reflector. Now, if you shine a red light on a white paper, then the paper itself will appear red. Also, a really cool thing about white paper is it fluoresces under UV light. So you can actually, so one of the laser experiments I did, I was making, I think it was 286 UV light from a near infrared laser beam. And so you can't actually see that wavelength of light with the human eye. That is much smaller than what we can see. However, I would use a piece of paper to find out where it was because it would fluoresce on the paper. And white paper works better than the expensive fluorescing things that you could purchase to look for the beam. So cool tangent. I think it's cool. Anyways. All right. So when light hits a transparent medium, some of it is reflected. So you always get a little margin of reflection. If you're doing a very precise optics experiment, you must calculate for that in your measurements. So I have done a variety of experiments really thinking about optics. So I've worked in laser labs. My thesis experiment was basically based on the optical properties of materials. So you always have to deal with the fact that you never have, or you very rarely have 100% you never have 100% transmission unless you're in a vacuum. But most of it most of the light will be transmitted through the material. Light will sometimes change direction when it's moving from one media to another. This depends on something called the index of refraction, which is right here. So the index of refraction is the speed of light in a vacuum divided by the speed of light in a medium. If you want it to have a really nice straight line from one to another, then you want this index of refraction to be the same. Then you won't get bending. If the index of refraction from one media to another is different, you will get some bending, and we'll get to that equation shortly. So this is why here we've got, if you are looking at fish in water, they will appear to you to look different from where they actually are. This has to do with the fact that light is being bent. Of course, there's the famous picture of the bent pencil in a glass of water. The pencil, of course, isn't bent. You're just seeing light slowing down in the water because the index of refraction of water is greater than that of air. And here's a really cool picture that was taken just to demonstrate the visual impact of the index of refraction between two media. So you have a duck on top in air and the water is on the bottom. And you can see the distortion. This is all related to the speed that light travels within these different materials. And here's the equation again. So you'll see this written a few different ways. C would be the speed of light in a vacuum. C sub m would be the speed of light in matter. Sometimes you'll see that written C over V. So the important thing is to just pay attention to whatever book you're reading. If you're like me and you like to dig back into historical books on the optical properties of media so that you can trace back their roots, like the cool person that you are, you'll see actually even different notation than that. Okay. So, this is where the laser pointer is. All right. So let's do an example. So the refractive index of Jell-O is about 3.5. Obviously, it depends on what type of Jell-O it is, but I did look this up because I wanted to give you an example that wouldn't be in a book. What is the speed of light in Jell-O? All right, so you have your index of refraction formula here. And so index of refraction is equal to C over the speed of light within the medium. We want to solve for C medium. So we get speed of light over index of refraction. This would make sense because that speed limit still exists. You can only slow light down. You can't speed light up. As far as we understand physics, if that's not true, then we don't know anything, which, that's always a risk in physics. We are never married to particular theories or even particular theorists. We are ready to throw stuff out at any time if there's a reason to. So then you would take 3 times 10 to the 8 meters per second divided by 1.35. Plug that into your calculator, you'll get 2.22 times 10 to the 8 meters per second. All right. So some common refractive indices. Vacuum is, of course, 1. Water is 1.33. So ones to memorize would be water and vacuum. Crown glass, which is a common type of glass, 1.52. Diamonds, 2.42. By the way, the refractive index of diamond being so high is part of what makes it so brilliant. So here you can see a diamond and it bends light in such a way that it looks spectacular. Air is 1.00029. Often, with air, you often round up to 1. Again, it just depends on the precision that you need. And for most applications in this class, 1 is precise enough. So I said that light will bend at the interface of two mediums if there's a different index of refraction. And this is because of something called Snell's law. So you have the incident light coming in. Let's see, I think I can draw this. That comes in just like that. I should have not picked red. And you're going to want to look at this angle with respect to the normal. That's going to be normal to the interface. So we've talked about normal vectors before. Let me do blue. Okay. And then this angle here, this is also incident to the normal. So this is the interface between the two the two medias and their different refractive indices. And so the index of refraction 1 times sine of the angle theta 1, so that would be that angle with respect to the normal is equal to n2 sine theta 2. And this is not, one thing to note, this is not from here, bad. This is from the normal. And so typically to measure the index of refraction, or one way to measure the index of refraction of an unknown media is to set up something like this where you can measure the angle coming out and then you can get the index of refraction. As long as you know the index of refraction and the angle that you're sending the light through, then you can measuring the angle at the other end, which is rather easy. You can then calculate the index of refraction. Or you could measure the index of refraction by doing a scattering experiment, which is what I did for my dissertation. It was appropriate for what I was trying to measure, but it's actually a harder setup. Okay, so measure the index of refraction of Jell-O, which we can see right here, then it's just easier to measure that, to model it as a straight line. And so the arrowhead is, of course, the direction of propagation. And so here's my joke. Grown on cue. No, Mulan, your reflection will only show the light reflected from the exterior. So it's never going to show what you are inside because your skin is opaque. I ruin everything. I'm so much fun to watch movies with. And by that I mean I'm not. Okay. So there is a law of reflection which states the law of the angle of reflection theta r is equal to the angle of incident theta I. So if you've got a mirror, whatever angle you set in, you'll get the same angle back. And so specular reflection is where you have parallel incidence rays that are parallel on reflection. So that would be a mirror would give you specular reflection. So here we've got specular reflection. And then diffused reflection means you have irregular reflection. So think about comparing like light to a mirror to light on a sidewalk. So with the sidewalk, you do get some reflected light, but it's diffuse. So it's being scattered in all directions. By the way, this works for acoustics as well. So before I did optics, I did acoustics. I'm all about the two main senses in my physics research. And so in terms of sound waves going through different media, you can get specular reflection, which means it bounces off cleanly, and then diffuse reflection, which means the sound wave is scattering in all directions. It's very good if you want to dampen a sound wave. So plane mirrors and rays. So rays can be figured out where an image will be formed in a mirror. So mirrors, a flat mirror like this is really easy to figure out. So where rays intersect or appear to intersect is where the image will appear. And we will go through how to do different ray diagrams. So with a plane mirror like this, your image will appear at the same distance as whence you are standing from the mirror. Now, there's certain rules for doing curved mirrors, which we'll get to. And light reflection, we see because light reflects. If light wasn't reflecting off of anything, those photons would not hit our eyes. We would not see images. So what we are always seeing is we are always and only seeing reflections. All right. So there's something called total internal reflection. So here's a picture of total internal reflection. So this is basically when light goes from a denser medium into a less dense medium. Light rays are refracted and bent away from the normal. And so when you have total internal reflection, it's a phenomenon which occurs when a propagating wave strikes the medium at the medium boundary at an angle larger than a particular critical angle with respect to the normal to the surface. So a weak reflection, you get just a little bit of light back. A strong reflection, you've got this critical angle, and you're getting a lot of light reflected back, but some is still going here. And a total internal reflection essentially means it's just being all reflected back. And so you get this perfect image that you see right there. So dispersion, the index of refraction will vary slightly with wavelengths. So light at different wavelengths are bent at different angles. So index of refraction is wavelength dependent. When you see those numbers, you're looking at typically the index of refraction for the average of the visible light spectrum. And so this process of bending lights at different angles is called dispersion. It's what allows us to see rainbows. It's how prisms work. I've already referenced the Sellmeier dispersion equation, which basically you could use then to get all of the different angles. To really do a good Sellmeier dispersion equation, you're looking at 9 coefficients. It's very cool and so beyond this class. All right, so in equations, you would have the index of refraction is c over the speed of the medium. the speed of the medium is equal to the wavelength times the frequency, so you can plug that in. Would be another way of calculating index of refraction. And like I said before, this is what allows us to see rainbows and double rainbows and triple rainbows. And yes, I have seen a triple rainbow before, and it is quite stunning. All right, so for lenses have different focal lengths that allow us to basically, cameras use lenses. If you wear eyeglasses, they have lenses, and they're basically focusing images onto hopefully a desired location. So for small angles, the deflection angle for any ray passing through a lens, a thin lens is y over f, where y is the distance from the axis where the ray hits the lens and f is the focal length of the lens. So here's the thin lens equation. So you want to make sure all the units are the same. So you have 1 over the focal length is equal to 1 over the distance from the object to the lens plus 1 over the distance from the lens to where the image is being focused. And you can calculate the magnification, so objects can be magnified or demagnified. So you would take the ratio of the height of the image to the height of the object. All right. Oops. So what is the position of the image of a 7.6 centimeter high leaf placed 1 meter from a 50 millimeter focal length camera lens? So here we've got our image. Pretty straightforward. So you have 1 over the focal length is equal to 1 over the distance to the object plus 1 over the distance to the image. Rearrange for the distance of the image. Oh, there's supposed to be a to the minus 1 right there. Let me draw that in. To the power of minus 1. And if you do that, then you get 0.52 meters for this particular setup. But that's how you use the thin lens equation. Yeah, you're dealing with a mirror that's curved, and they're really useful for focusing light in different ways. And so what you're looking at is a section of a sphere that has some radius r. So r would be the radius if the mirror continued to curve all the way around to make the sphere. I draw even worse with this. The principal axis is a line drawn through the center of the curvature. Here you can see this particular image. They're calling it the optic axis. That's just another word for it. So the center of the curvature is C. So you want to draw a line through the center. The vertex is the point where the principal axis and the mirror meet. So here's our vertex right here. And the focal point is the point which the rays meet after reflection. So here is our focal point. So this mirror is going to focus an image right here. And the focal length is the distance. So here's our focal length. So we've got a couple different things with mirrors. Vertex, focal point, focal length, and R, radius of curvature. These are all important to drawing diagrams of where images will appear using spherical mirrors. So there are two types of spherical mirrors. Concave, which is a converging mirror. So this is a mirror that curves in when the light is reflected and it converges to a focal point in front of the mirror. So here you've got a concave mirror. So that would be spoons are very useful because they have both concave and convex mirrors. So if you look at the curved side of the spoon, which you use to scoop up yummy, yummy Jell-O, then you'll get a concave mirror. And then a convex or diverging mirror, the mirror that curves out when the light is reflected and the rays appear to diverge. So the focal point will be behind the mirror. So here we would have a convex mirror. And yes, you can flip yourself upside down by looking into a spoon. All right, so, and what you're dealing with here, so this is, again, this is a trick that the eye is going to play on you. So it will appear, in a convex mirror, it's going to appear behind. It's going to appear behind the mirror. Okay. So to do a ray diagram, I actually do not like how your book does this. Use these slides instead. Pick a point on top of the object. So typically you draw your objects as arrows because that's easy. Now, if you take an optics class, you'll need to do ray diagrams with rulers, and you need to have some level of precision. In this class, I just want you to know the rules. So you pick a point on top of the object and draw 2 incident rays. So your first ray, let me change colors to orange. Your first ray is going to go from the top of the object. You want to draw it straight, so don't do what I'm doing. Top of the object to parallel to the center line. And then the other should intersect the focal point. So these are the 2 lines that you want to draw. I'll just circle them next time. All right, so then once the lines strike the ray, the mirror is going to reflect them, and you're going to use these 2 rules. So what you're looking for is where the image is going to show up. So the line that has been parallel to the center, you want to reflect that then through the focal point. Right there, and the line that has gone through the focal point now runs parallel. And then where these 2 intersect is where the image will appear, and you can see that the image is going to appear upside down. So then typically what you do is you draw a little arrow. And so it's going to be demagnified and upside down. So, and these are the rules. The 2 rules of reflection for concave mirrors. Any incident ray traveling parallel to the principal axis on the way to the mirror will pass through the focal point upon reflection. Any incident ray passing through the focal point on the way to the mirror will travel parallel to the principal axis upon reflection. So this is the point where I would normally bring students up to the front and have everybody practice. I would recommend you stop the video and practice this and then move on. All right, so for a convex mirror, we've got step 1, pick a point on top of the object and draw 2 incident rays. So note I've got the focal point drawn in here. 1 ray should travel towards the focal point and draw the second ray so that it is parallel to the principal axis. So in this case, you kind of want to get a sense of what it would do, what angle it would come in order to intersect the focal point. So this one runs parallel, and this one is going towards the focal point and would intersect if it kept going. Step 2, once these incident rays strike the mirror, reflect them according to the 2 rules of reflection. So the line that was parallel then is reflected so that its tail, so typically you'll see like a dashed line showing that it would go to the focal point, like what I'm trying to draw there. And then the ray that was going towards the focal point then reflects parallel. Okay. Locate and mark the image of the top of the object. The top of the image is where the 2 lines intersect. So then you'd want to do the same dotted approach. This one would continue back this way. So basically you are continuing the 2 reflected rays as though they were going behind. So in this case, your image would be here, which you can see in the picture down below, and you can see that it has been demagnified but is upright. So the top of the image is where the 2 lines intersect. This is a virtual image, so it can't be projected onto a screen. So I'm going to read the 2 rules again. These rules represent slight revisions of the 2 rules given for concave mirrors. The revised rules can be stated as following. Any incident ray traveling parallel to the principal axis on the way to a convex mirror will reflect in such a manner that its extension will pass through the focal point. Any incident ray traveling toward a convex mirror such that its extension passes through the focal point will reflect and travel parallel to the principal axis. And once again, I recommend that you stop the video and practice drawing a convex mirror ray diagram. We're not looking for precise measurements right now. We are looking for general ideas. Once you get the general idea, then you need to practice the precision. As opposed to this one, which bulged out at the center. So, pick a point. Once again, you've got 3 lines. Pick a point on the top of the object and draw 3 incident rays traveling towards the lens. So the first one is going to be parallel. One is going to be traveling through the focal point on the other side, and one travels parallel and then the other one is going to go through the center of the lens once again. Once these rays strike the lens, refract them according to the 3 rules of refraction. So, for the one that is parallel, it is going to refract, and you're going to, once again, you'll be drawing backwards. So you're going to have the tail of it go towards the focal point right here. The one that was going to the focal point on the other side now goes parallel, and you'll actually continue the back of this ray as well. And the one that goes through the center just keeps on trucking through the center. And you're going to look for the intersection of these 3 lines. In this case, it's going to be here. So it's going to be in front, and it's going to be smaller and vertical. All right. So here are the rules. To draw these ray diagrams, we will have to recall the 3 rules of refraction for a double convex lens. Any incident ray traveling parallel to the principal axis of a diverging lens will refract through the lens and travel in line with the focal point, i.e. in a direction such that its extension will pass through the focal point. Any incident ray traveling toward the focal point on the way to the lens will refract through the lens and travel parallel to the principal axis. Any incident ray that passes through the center of the lens will in effect continue in the same direction that it had when it entered the lens. And again, I recommend stopping the video and practicing these ray diagrams, because I will ask you to give me ray diagrams for both types of mirrors and both types of lenses that we talked about. And there are even more ray diagrams than this that you can do, and you get to draw lots of ray diagrams in an optics class. It's tons of fun. Okay, so in optics, a real image is an image which is located in the plane of convergence for the light rays that originate from a given object. If a screen is placed in front of the plane of a real image, the image will generally become visible on a screen. So in this case, you've got a real image that this would show up on a screen. So images from projectors are examples of real images. So basically, real and virtual just means, will it show up on a screen or will it not show up on a screen? A virtual image is an image formed when the outgoing rays from a point of an object always diverge. So we've drawn a couple divergent ray diagrams. So here you have a divergent ray diagram. So you can see you're dealing with the tail ends of the rays. So you can perceive this image with your eyes, but you cannot project it onto a screen. The image will appear to be located at the point of apparent divergence because the rays never really converge. A virtual image cannot be projected onto a screen. So you can see virtual images, you cannot project them onto a screen. And the human eye, this is how we perceive images, and I'm sure all of you have taken many classes on the human eye, so I'm just going to touch on a few things. It contains a convex lens with other refractive material, and this is where most light refraction occurs. So if you've got an eye that sees 20/20, you've got everything in terms of the refractive material has lined up so that you get the image that's focused on your retina is in focus. It's exactly where it should be. So it's focused on the retina, which is made of photosensors called rods and cones everything's working correctly, then the light that you're seeing reflected into your eye is focused perfectly where you can interpret it by your brain. And basically a vision defect related to the refractive materials within your eye basically means that your image is being focused at the wrong focal point. So for example, I'm very, very nearsighted. That means that my eyes are focusing images somewhere in the middle of my eye, and so I'm seeing a fuzzy image in my retina. I'm not seeing an image that's in focus. And then if you're farsighted, it means that the refractive material in your eye is actually focusing it behind your retina. So there you go. So that is the rest of chapter 23. And we will start your next lecture. We'll start to get into supplemental 3. You can find that for free on the Matter and Interactions website.